Hello everyone, welcome to the channel. I hope you all are doing great. So from this video, we are starting with the new series which will be the previous year questions of the CSIR NET exam. From the year 2011 to the 2025, we are gonna discuss all the questions. Okay, so firstly, we are starting is with our first chapter, that is the kinetics, and this video is gonna be the part number 1 in this. So this is the part number 1. Okay, so before starting the video, if you are coming to the channel for the first time, make sure you subscribe to the channel and do hit the like button also for the video if you understand the concepts, and do share it with your friends as well. So let us begin with the first question. So this is from your year CSIR June 2011 exam. Okay, so the first question it says the half-life for a zero-order kinetics, a zero-order reaction, which is A to B, is given by. Simple question, thus the half-life expression it is being asked for the zero-order reaction, zero order. We know the integrated rate expression is A naught minus of A, this is equal to the KT, right? For the half-life, we know that A, which is the remaining concentration, it is equal to the A naught by the 2 because 50% of the reaction is completed at the half-life. Substitute this in the above expression. So we have is A naught minus of the A naught by the 2. This is equal to the K T half, right? This will be A naught upon the 2 K. This is your T half for the zero order reaction. That is A naught upon the 2K. So the correct answer will be the option A in this case, right? Next is we have this. So again, it is from the same paper only, which is from the year 2011, conducted in the June. Okay. So this question it says the decomposition of the gaseous acetaldehyde, it follows a second order kinetics. So kinetics which is being followed is given. The half-life for this reaction is 400 seconds when the initial pressure of it is 250 torrs. Now, for a second order kinetics, for the second order kinetics, the integrated rate expression we have is that is 1 by A minus of 1 by A naught. This is equal to the KT of it. For the half-life, A value will be equal to the A naught by B2, which is the remaining concentration for the half-life. 50% of the reaction is completed, so the remaining concentration will be A naught by B2. So substitute this in the above expression, A naught by B2 minus of 1 by A naught. This is equal to the KT half, right? So this will become 1 by A naught into the K, that is gonna be the T half for the second order kinetics, right? So now here they are given that half-life for this reaction is given and the initial pressure is also given. So they are asking what will be the rate constant in these minutes. Okay, so the rate constant K, we can write it like this, 1 by A naught into the T half of it, because just take this, rearrange this expression and you are gonna get the rate constant values. Now A naught it is given to us as 250 torrs and the time, that is half life, is your 400 seconds. Substitute this, the rate constant it is gonna be 250 torrs into the 400 seconds. Now 25 fours are is 100 and 3 zeros are this one. So overall it becomes 10 raised to the power of 5 in the denominator, which is going in the numerator and becomes the 10 raised to the power of minus of 5. So this is gonna be the rate constant value. Okay, this is my rate constant minus of 5. Right, so the first part we have solved it. Next is half-life. We have to find it out. If the initial pressure is 200 torrs. Okay, so now this time the initial pressure is different. So if A naught value is 200 torrs, the reaction is still the same only. So the rate constant is gonna remain the same only, which is torr inverse second inverse. So T half value, this will be equal to 1 by A naught into the K of it, which will be 1 by 200 into the K value, which is 10 raised to the power of minus of 5. So this becomes 1 by 2 into 10 raised to the power of minus of 3. So this becomes the 1000 upon 2, which will become 500. So time will be your 500 seconds. So T half when the initial pressure is this much is your 500 seconds. So 10 raised to the power of minus of 5 and 500 seconds is given to us in the option B. So B is the correct answer for this one. Okay. Next is we are having this question. It says for an enzyme catalyzed reaction, the line Weaver Burke plot. So this is the plot for the 1 by R versus the 1 by S. Gave the following data that slope value is this much and intercept value is this much. If the initial concentration of enzyme is this much, what will be the catalytic efficiency? That is eta. Okay. Now for an enzyme catalyzed reaction, the rate expression that we get, that is R is equal to R max into the S upon the Km plus of the S. So this is the rate expression where R max, this is the maximum rate, which is K2 into the T naught of it. How is the reaction taking place? Enzyme plus the substrate, they both are combining, forming the intermediate ES. Rate constant is K1, this is K inverse of it, and then in the second step ES, it gets converted into the final product with the rate constant K2. Okay, so this is R max value, S is the substrate. So now 1 by R versus 1 by S, we wanted to just reciprocate this expression of the rate that you are having. So it will become 1 by R, this is equal to Kn plus of the S upon the R max into the S, right? This on expansion, it will become Kn upon the R max into the 1 by S upon the 1 by R max. So this is gonna be the expression that is equal to 1 by R. Just related to a straight line equation, y is equal to the mx plus of bc. So 1 by r versus 1 by s, the plot if we are seeing, the slope value we are getting it as km upon the r max of it, and the intercept value we are getting it as 1 by r max. Right? Now the slope and intercept values are given to us. So km by the r max, this is equal to, this is the slope value and slope is given to us as 40 seconds. Right? Now Kn, now Rmax is nothing but the K2 into the E naught of it. This is equal to 40 seconds. Right? Now from here we can find the value of K2 by the Kn, which is nothing but your eta, which is called as the catalytic efficiency. This is my catalytic efficiency, which is K2 by the Kn, that will become your 1 by 40 into the E naught value. So E naught, which is the initial concentration of the enzyme, that is also given to us as 2.5 into 10 raised to the power of minus of 9. So that you can substitute it. So this decimal, this will get cancelled. 25 fours are is 100, which becomes 10 raised to the power of minus of, concentration is 10 raised to the power of minus of 9 only. So 10 raised to the power of minus of 7, bringing it into the numerator, it will become 10 raised to the power of 7 of it, right? So that means the catalytic efficiency we are getting it as 10 raised to the power of 7. So the answer we are having is, it's given in the option C. Okay. Next one is this question. It says, observe the following aqueous solution of the same compound. All the measurements are made at the same wavelength and at same temperature. The three of the solutions A, B and C different data have been provided to us. The optical density of these solutions, it follows the order. Optical density, it means they are talking about the observance. This is the observance value. So for the first solution, we have been given the transmittance of a zero point 0.1 mole per decimeter cube using the 1 centimeter length. It is zero point 0.5. So here the transmittance value it is given to us as zero point 0.5. We know that observance, this is equal to the negative log of this transmittance value, that is negative log of 0.5. So we can find the value of this one and we are gonna get the observance value, right? So this negative log of zero point 0.5 we are having, that you can write it like this one, it will become 10. So 1 by 2 it will become, right? So that is becoming the log 2 value which we know it is 0.3010, right? So this is the observance value that for the solution A we are gonna get it, right? Now next solution it is the optical density of this much concentration solution we are having is measured using the 1 mm cell. Okay, the optical density of this much. So observance value we know it is equal to epsilon c into the length of it. This observance value we have to find it out. This is epsilon. The concentration it is zero point 0.5 mole per decimeter cube and the length value it is given to us as 10 raised to the power of minus of 3 meters, so that you can convert it into the centimeters. So this is the optical density formula we are having. So something is missing over here, that epsilon value it is not given to us. So we won't be able to find the observance value in this case. Some data might be missing in this. So sorry for the inconvenience for this one. Okay, so let's leave this one. For the solution C, if you see the transmittance of the solution, it is zero point 0.1 we are given. So observance is negative log of this value, which is zero point 0.1. So this comes out to be as the unity. So maximum observance you will be seeing, it will be for the solution A, followed by the solution solution C is the maximum, followed by the solution A, and the least will be for the solution B. So might be some other data that is for the epsilon it is missing, but this is gonna be the order. So the correct answer in this case it's gonna be the option B. Okay. Next one we are having is this question. So these were all the questions that was from the June 2011 exam. Now for the December 2011 exam, let us see all the questions. This question it says the rate constant of a unimolecular reaction, it was found to be this much and this much as the temperature 120 Kelvin and 360 Kelvin respectively. What is gonna be the rate constant at 240 Kelvin? So we know that temperature that you this rate constant at the other temperature conditions, that is T2 upon the temperature at the first temperature conditions, this is equal to the pi raised to the power of delta T by the 10. So here delta T value it should be the positive one. So which will be T2 minus of T1. This is gonna be positive, which means the T2 that you will be keeping it will be greater than the T1. Okay. So the rate constant at the other T2 temperatures, we can consider the higher temperature which is of the 360 Kelvins. The value of the rate constant we have is 2.2 into 10 raised to the power of minus of 1, and the temperature T1 which is at 120 Kelvins, the temperature we are having it at, the state constant value is 2.66 into 10 raised to the power of minus of 3. This is equal to your 5 raised to the power of, now the temperature change, that is 360 Kelvins minus of the 120 upon the 10, right? This will become 5. This will be equal to the 5 raised to the power of 240 upon the 10. That means 5 raised to the power of 24. This much value you are having. So 2.2 into 10 raised to the power of minus of 1 upon 2.66 into 10 raised to the power of minus of 3. So using this data, you can find the values of the 5, which is the temperature coefficient, right? So the 5 value we are gonna get it as, solving this, the 5 value you will be getting it as 1.2, right? Now this temperature coefficient you are knowing it. Some other temperature which is at 240 kelvins, the rate constant you have to find it. You can use one of the data which is for at the temperature 120 kelvin. Suppose if that is given to us, that data we can use it. So rate constant at 240 kelvins we have to find it upon the rate constant which is at 120 kelvins. This is again gonna be equal to the 5. The temperature change, which is now 240 kelvins minus of the 120 raised upon the 10, right? So substitute these values which are known to us. So the rate constant at 240 kelvins we have to find it out. At 120 kelvins we are having the value as 2.66 into 10 raised to the power of minus of 3. 5 value we are having it as 1.2 that we have calculated. Now the temperature change, this is of the 12, we will be getting 120 upon the 10. So 10, 12 the power it will become, right? So solving this, the values of the rate constant at 240 kelvins, we will be getting it as 1.2 raised to the power of 12 into the 2.66 into 10 raised to the power of minus of 3. Answer we will be getting it as 2.4 into 10 raised to the power of minus of 2. So this is gonna be the rate constant value at the 240 Kelvin temperature. Okay. So the answer is the option 2.4, that is in the option A, it is given to us. Right. Next is we have this question. It says the overall rate of the following complex reaction. So the reaction that is given to us is 2A is in equilibrium with the A2, which is K1 upon the K2. A plus B, this is in equilibrium with the C at the rate constant K2. This will be K inverse in the above reaction. This is K inverse. Okay. And A2 plus the C, this is giving you the equilibrium with the P plus of the 2A, that is with the rate constant K3, and this is the slowest step of the reaction, and these two are the fast equilibriums. Fast equilibrium. So approximations we are gonna use to find the rate of this reaction. So rate of reaction depends upon the slowest step of the reaction. So rate will be K2 into the various concentration terms, which is A2 and the C, right? So now A2 and C, these both are the intermediates which are formed during the course of reaction and are also getting being consumed during the course of reaction. So these two are intermediates. Always the rate we are writing it, it will be in the terms of the reactants only, right? So A2 concentration we can find it using this fast equilibrium, that is the rate constant K1 upon the K inverse. This will be equal to the product, which is A2 upon the reactant, which is A, and its power will be the 2, which is the stoichiometry that is given to us. So from here A2 value we are getting it as K1 upon the K inverse into the A square. So this is gonna be the A2 concentration. And for the C's concentration, using this equilibrium, we can find the rate expression. The C concentration, K2 will be equal to the product concentration upon the reactant, which is A, and the P1. So C's concentration, it is K2 times the A into the B of it. So this C's concentration and this A2 concentration, this you can substitute in your rate expressions. So rate it becomes the K2 into the A2, which is K1 upon the K inverse, right, into the A square, and the C's concentration, which is K2 into the A into the B's concentration, right? So this is the expression for the rate that we are getting it, right? So this is the one. So here a bit mistake I made. Here the rate constant in the final expression it is K3 because here the rate constant for this step it was K3. So here instead of K2 it will be K3, right? So this is the one we are getting. So here overall power of A it becomes A2 and the one which is A cube it is becoming and the B it is becoming. So K1, K2 and the K3. So K1, K2 and the K3. Instead of K1 by the K inverse they have just written as K1 only. So that only you can substitute it. So rate expression is this one. So main is about these powers which are present in terms of the A and B that we are getting, which is A cube and the B that is given to us in the option A, right? Next is we are having this the concentration of the reactant undergoing the decomposition was these data has been given after the time of 1 hour, 2 and 3 hours respectively. What is the order of this particular reaction? So to solve this question, you have to use is the integrated rate law expression, integrated rate law expression we have to use it. So here the data is given and the time intervals are given. Data we are having it as zero point 0.1. This is after 1 hour. 0.08 that is after the 2 hours and we are having 0.067 that is after the 3 hours. So in the integrated rate law expression what we do is we take this data and find the rate constant for the different orders of the reaction. If the rate constant value we get it to be the constant in the data that we are using, then that particular order of the reaction is the obeyed. For example, firstly let us check this one for the zero order. For the zero order kinetics, the integrated expression we have is A naught minus of A. This is equal to the Kp. So A naught we can consider this is the initial concentration which is your 0.1. The remaining one is this one which is 0.08. Time span you are having is of 1 hour. So this is K into the time, right? So solving this 0.02 is gonna be the rate constant that we are getting from the first data, right? Now the next time using the same integrated expression, but this time using this one and this particular data. So in that case, A naught minus of the A is equal to the K3. So A naught is again 0.1. This time A value is 0.067. This is equal to the rate constant K. The time span 1 to 3 it is of the 2 hours. Right? So solving this, the rate constant value we will be getting it as 0.33 value you will be getting. So K value will be divided by the 2. Solving this, we will be getting 0.0165 as the rate constant. So if you see the rate constant value in one case it is 0.02 and the other time it is 0.0165. So the different rate constant values you are getting. So that means K is not the constant one. So the reaction is not following the zero order kinetics. It is not following the zero order kinetics. So what you do is after the zero order, instead of going to the first order, check it firstly for the second order reactions. For the second order, the integrated expression we have is 1 by A minus of 1 by A naught. This is equal to the Kp. So now 1 upon the A value which is 0.8 minus of 1 by A naught which is the 0.1. This is equal to the Kp. So this comes out to be as 12.5 minus of 10. This is K. The time span will be of the 1 hour K into the 1, right? So rate constant we are getting it as 2.5. This is the first one. Now using the other data that is of 0.1 and 0.067. So again expression is this one only. Find the rate constant 1 upon 0.067 minus 1 upon 0.1. This is equal to k. This times the time is of the 2 hours. So solving this, the rate constant value we are getting it as 2.46, which is approximately equal to the 2.5 only. So you see the rate constant in both of the scenarios you have got to be the same only. That means the rate constant k is constant. So the reaction is following the second order kinetics. The reaction is of second order kinetics. So this is how the integrated rate law expressions have to be used. That means the order of the reaction is second, which is given to us in the option C. Alright. Moving upon to the next one we have is this. So it says at any temperature for the following reaction where deuterium T and T are the deuterium and tritium respectively, the correct statement is, so the reaction we are having is HCl is combining with the fluorine to give us the HF and the CH. Similarly, the isotopes of the hydrogen, which is deuterium and tritium, they are combining with the fluorine and forming the DF and the TF instead of the HF now. So what actually is happening is this HCl bond that I am having, it is combining with the fluorine. So this bond is breaking over here, right? So the bond breaking. So we know this thing that stretching frequency it is equal to 1 by 2 pi into the root of k by mu of it. So k is the force constant and mu is the reduced mass. In case of the HCl, the BCl and the TCl, the masses comparison if I see tritium has the maximum followed by the deuterium and least masses for the hydrogen. We know the stretching frequency it is inversely proportional to the reduced mass. Higher is gonna be the reduced mass, lower is gonna be the stretching frequency. Whereas lower is this reduced mass, more is gonna be the stretching frequency, which means the breaking of the bond it will become to be the easier in that case. So we can say lower is the mu, more will be the stretching frequency, more will be the mu value and easier will be the bond breaking. Easier will be the breaking. Bond breaking. One more plot you might have seen like this one. Here for the this is the dissociation that is taking place. These three lines that we are drawing. So the energy levels that you have. This higher one it corresponds to the high HCl. This one will correspond to the DCl and this corresponds to the PCl. This is the energy versus energy plot. Energy is on this side. So you see HCl it has the where the distance it is there. HCl it has the highest energy, which means it is the weakest bond you are having. So it can easily break because that is what is happening in the given reaction. Right? So out of the A, B and C, A is the one in which the HCl is gonna break at the fastest rate. So A is gonna give the fastest reaction. So the option A will be the correct in this case. Okay. Moving upon to the next, this one. It is an example of the relaxation method of measuring the rates. So these are the actually for the fast reactions. So these are fast for the fast reactions. So for the fast reactions to study these various methods generally we use. First one you have is that is called as the spectroscopic method. Spectroscopic methods are used. Next we have a stopped flow technique. We have a stopped flow technique. What is this stopped flow technique? So here what you do is you have two of the reactants. Suppose this is the reactant A. From this inlet you are providing and from the other inlet you are providing is the reactant B. Both of them they are brought from the tubes and they are made to meet in one of the tubes like this. So these both are flowing into it. Okay. So from here the reactant A is coming and from here the B is coming. So both of them they are coming and mixing in one of the tube only. This is the one which is going. So what you do is you all of a sudden you stop the flow of these reactants. That is basically a jerk is provided to study the fast reaction, which is called as the stop the flow method. So the reactants A and B, they both are coming and they are stopped at once only. This is in the stopped flow technique. Next technique we have is that is called as the temperature jump, and the other one we have that is called as the pressure jump. This is called as pressure jump. So what you do is you are having two of the reactants A and B. These both are brought to one of the containers where the A is coming and B is coming, and this they both are reacting to form some product. P, suppose they are forming it. So what is gonna happen after some time? It is not always the reaction is gonna go in the forward, and equilibrium will be established between them like this. The equilibrium is being established. So after some time, what you do is at a particular temperature, suppose T Kelvin, this equilibrium is established. So what you do is you all of a sudden change the temperature. Okay. So due to that, what is gonna happen? This equilibrium that you have established, it is gonna be this. It will be disturbed, right? So in that case, the reaction will again start, and it will go until a new equilibrium is getting being established. So temperature is changed suddenly. Temperature is changed suddenly to disturb this equilibrium, to disturb the equilibrium, to disturb this particular equilibrium. So after some time, a new equilibrium will be established. So the time gap that you are having between this equilibrium which was established and the new equilibrium that is getting being established after the temperature change we have brought it, that is what is studied in the temperature jump method. And this time gap, this is called as your relaxation time, and the method's name is relaxation method. Okay. So this is the time difference that you will be having. This is called as the relaxation time. That is time between this equilibrium and the new equilibrium is established. Equilibrium established. Okay. So this is called as the relaxation method. So we are having this temperature jump experiments for this. Similarly, like we are bringing a sudden change in the temperature, you can do this sudden change in the pressure conditions also. At that point, the pressure will be changed at one of the equilibrium you are having, you change the pressure. So to the new pressure and equilibrium again it is gonna be established. So the time gap between them it's gonna be called as the relaxation time, and this is also your one of the relaxation methods. Okay. So either we can perform the temperature jump experiments or the pressure jump experiments to study the relaxation method. Okay. Next is, so these were all the questions from your December 2011 exam. With this, your first year, that is of the 2011, all the questions we have discussed. Now, it is for the June 2012 exam. The question it says that for a reaction, the rate constant at 27 degrees centigrade it was found to be this much. What is the activation energy of the reaction? So this is from your Arrhenius equation. We have as rate constant A, this is equal to A into e raised to the power of minus of EA upon the RT of it. This is your Arrhenius equation. So the rate constant now K that is given to us, it is 5.4 into 10 raised to the power of 11 e raised to the power of minus of 50. So just compare these two equations. You are getting it as EA upon the RT. This is equal to the 50. We have to find the activation energy. So EA will be equal to RT into the 50, which is equal to 8.314. This is joule per mole per Kelvin into the temperature, which will be 300 Kelvins. Okay, and this is 50. So with this Kelvin, this per Kelvin will get cancelled out. Overall activation energy we will be getting it into the joules, which we will be getting it as 124710. So this is approximately, we can say, the closest answer, which is 125,000 joule per mole per Kelvin of it. Joule per mole, sorry. Okay, so the correct answer is the option B in this case. Right? Next is we have this one. So it says the rate law for one of the mechanisms of the pyrolysis of this acetaldehyde at this much temperature and pressure is given. What is the overall activation energy? So the rate constant value that you are having, the overall rate constant, that is K2 into the K1 upon the 2 times of the K1 raised to the power of half of it. Okay, so it is not the 1, it is the 4 over here. 2K, 4 it is there. Okay, so this is the rate constant. So what you do is take the natural log on both the sides. Natural, taking ln on both sides. On both sides. We are having is natural log of k. This is equal to the natural log of k2 plus of the half of natural log of k1 minus of natural log of 2k4, that you can write it as m into the n. So this we can write it as natural log of 2 minus of the natural log of k4. Like this it will be written. Now differentiate this with respect to the temperature. So here we will be getting d ln of the k. So this one we will be having it as d ln of the k, ln of the k upon the dt. This is equal to d ln k2 upon the dt plus of the half of d ln k1 upon the dt, right? And this one is going to be natural log of 2. It is your constant with respect to temperature. If you are differentiating, that is going to be 0 minus of 1 by 2 into the d ln k4 upon the dt of it. This is going to be the differentiating values. Now we know that d ln k by the dt, this is equal to the minus of the EA upon the RT square. So this is of the overall one. This is equal to, now d ln k2 by the dt, this will be activation energy 2 upon the RT square. Here a negative sign it will be there. Next is plus of the plus of half of minus of the EA1 upon the RT square, and this is gonna be the plus of 1 by 2 EA4 upon the RT square. Right, taking negative from all the sides and the denominator RT square, you can cancel it out. So activation energy overall we will be getting it as EA2 plus of this, because negative you have taken it out from this one, so it will be EA1 upon the 2 minus of the EA4 upon the 2. So this is the overall activation energy that we will be obtaining. So EA2 plus EA1 by 2 minus of the EA4 by D2, that is in the option C we are having it. Alright. Next one we have is this question. So this is again from your enzyme catalyzed reaction. It says in the Michael-Menten mechanism for the enzyme kinetics, the expression obtained is this one we are having it. The values of the K3, KRMX, this K is respectively R. So this K3 and the Kn value you basically have to find it out. So for the enzyme catalyzed reaction, we know that the rate R is equal to the R max into the S upon the Kn plus of the S of it, right? To the cross multiplication of this, R into the Kn plus of the R into the substrate S, this is equal to R max into the S of it, right? Now R max we know this is equal to K2 into the E naught of it, E naught FTS, this is equal to R Km plus of the R into the substrate S of it. take this E naught into the S in the denominator because in the given expression it is there. So we get is R into the Km upon the E naught into the S plus of the R upon the E naught. This S and S value it will get cancelled out, so that you can write it like this. This is equal to the K2 value, right? So if you compare this, now Km you can bring it in the denominator, or we can say this R into the Km upon the E naught into the S. This is equal to K2 minus of this R upon the E naught value, right? So this we are getting. Now this Kn, if I bring it in the denominator, it will be R into the E naught into the S. This is equal to K2 upon the E naught of it minus of 10 this R upon the minus of R upon the E naught into the Kn of it. Here also it was K2 by the Kn of it. This is the expression we are getting. Now here instead of this R, the V term is just being used. So you can replace with that V upon the E naught into the S. This is equal to K2 upon the Kn minus of the V upon the E naught into the Kn of it. This we can write it like this. Okay. So now compare this expression that we have obtained with the given expression. So you will be getting the values that V upon E naught into S, this is equal to K2 by Km, that is equal to 1.4 K2 by the Km. This value is equal to 1.4 into 10 raised to the power of 12 of it. And this value, that is 1 by Km value, this is equal to 10 raised to the power of 4 of it. So compare these two. Okay. So Km value from here we are seeing it is equal to 10 raised to the power of minus of 4. So this was one of the thing we had to find, that is the Michael-Menton's constant. Okay. And this they are saying is K3. So this K3 is nothing but in the derivation that we have been doing, this we generally write it like this. E plus S is in equilibrium with the ES, that is K1, and this is K inverse, and ES giving you the product P, this is K2. Now instead of the K inverse they have used this K2, and instead of K2 they have used this K3. So this is just the difference. So we are finding the values of the K2 over here. K2 upon the 10 raised to the power of minus of 4. This will be 1.4 into 10 raised to the power of 12 of it. So from here the K2 value you get it as 1.4 into 10 raised to the power of 8 of it. Okay, so this is the K2 and the Km values that we were to calculate. 1.4 into 10 raised to the power of 8 and Km is 10 raised to the power of minus of 4. The option C will be the correct answer for this. Right? Next one you have is this question. The molar extinction coefficient of a B which is having the molecular weight of this much, it is this value we are having. 1 liter of the solution C which is containing this much grams of the pharmaceutical preparation of the B, it shows an observance of 0.441 in a 1 centimeter quartz cell. What is the percentage weight by weight of B in the pharmaceutical preparation? So what they have done is they are having some compound which is B, they have labeled it, whose molecular weight it is given to us, and its absorptivity, molar absorptivity, it is given as the molar extinction coefficient also you can say. This value is given to us. So using this compound, they have prepared a solution which they have labeled as C. So C solution has been prepared in which the B has been added. So what B amount they are adding is, this is 0.1358 grams of it. Okay. So they are adding it 0.1358 grams of it. This solution that they have prepared, it is showing the observance value of how much? 0.441. Okay, and with the quartz cell which is of the 1 centimeter, they have measured this much absorbance. So what is the percentage weight by weight in this pharmaceutical preparation, which means to say is this absorbance value that you are getting, in that how much amount of the B component is getting being involved. We are thinking that this whole of it B is giving us this absorbance. So is it true or not? How we will be doing this? We will be finding the concentration from this absorbance value. Okay, from that we will be seeing how much amount of the B is showing us this absorbance value and how much amount of the B we have added. Their ratios, it is gonna give us the value of weight by weight, which means how much amount it is showing the absorbance and how much amount we added to it. Okay, I hope the concept is clear. So now the absorbance value we know it is equal to epsilon C into the L of it. Absorbance value it is 0.441, right? The absorptivity value it is given as 4 into 10 raised to the power of 3, which is mole inverse liter per centimeter of it, right? Now the concentration value we are having it as this, we have to find it out, and the length we are having it as 1 centimeter. So with this centimeter, this per centimeter term will get cancelled out. You will be getting the concentration in mole per liter terms, right? So concentration it will be 0.441 upon 4 into 10 raised to the power of 3. This will be getting it as mole per liters, right? So this one mole per liter concentration. So this you can equate it because we need to find is the weight of it. So this is concentration is number of the moles of the solute upon the volume of the solution that you have prepared, volume of solution in liters. This is equal to your this much concentration, which is 4 into 10 raised to the power of 3. This is mole per liter. From here, if you see the volume of the solution, it is given us as 1 liter, which means the number of moles that we are gonna get here, it is 0.441 upon 4 into 10 raised to the power of 3 of it. These many number of moles of the B it is present in my solution, right? Now number of moles we know it is given weight upon the molecular weight of it, molecular weight, which we will be getting it as 0.441 upon 4 into 10 raised to the power of 3 of it. Now molecular weight of the B it is known to us, which is 180. So the given weight we can find it out. So the weight it will be 0.441 upon 4 into 10 raised to the power of 3 into the 180 grams per mole of it. So these are the moles we were having. So with this mole, this per mole will get cancelled out. That means how much amount of the B it is present in the solution in the grams. We are getting this as, so this we are saying it is given weight. This is equal to 0.19 grams of it. So how much B we added was in the preparation, this was 0.1358, but in the solution how much absorbance, based upon the absorbance, how much of the B was involved, that is this much. So percentage of the weight by weight, that is gonna be equal to 0.019845 upon 0.1358. Multiply this with the factor of 100 to find the percentage, that we get is as 14.6%. So this is how the weight by weight percentage of it has to be calculated. Okay, so the correct answer becomes the option B in this case. I hope the concept is clear. Moving upon to the next one, we have is this question. It says one of the assumptions made in the conventional activated complex theory. So according to the activated complex theory, an equilibrium is present between the reactants and the activated complex. That is A plus B, suppose they are reactants, there is an equilibrium with the activated complex which is getting formed between them. So the correct statement is an equilibrium is maintained between the reactants and the activated complex. That is the option A. Next is we have this one. It says a carbon 4 activity of the old wood sample, it is found out to be this much disintegrations per minute per gram of it. Calculate the age of the old wood sample if the fresh wood sample of the carbon 14 activity is this much. So we have been given the activity initial one and the remaining activity has been given. T half for it is also given to us. Okay. So this is from the radioactivity concept. So first order kinetics is being obeyed. For the first order, we know A is equal to A naught times E raised to the power of minus of kT of it, where A is the remaining concentration, that is the remaining concentration, or instead of that, we can also use the term activity, and the A naught, that is the initial concentration, right? So the A value where we are having it, that is 14.2 disintegrations per minute per gram, that is given. The initial one, that is a fresh sample of the wood, it is gonna give us the disintegrations, that is 15.3 disintegrations per minute per gram of it. This is E raised to the power of minus of 8. This time period we have to find it out. So we need is the value of this equilibrium constant for this. For the first order, we know that T half value it is 0.693 by the K of it. T half of the carbon it is already given to us. So this is the T half value which is 5730 years of it. So from this the rate constant value it is gonna be 0.693 upon the 5730 years of it. Okay, substitute this K value in the above expression. So you will be getting 14.2. This is equal to 15.3 into E raised to the power of minus of 0.693 upon the 5730 into the time t. So just solve this and find the value of your time period. So 14.2 upon the 15.3, this is the natural log, will be equal to minus of 0.693 upon the 5730 into the time t. So from here, the t that we will be getting it as 617 years you will be getting it. So this is gonna be the answer which is in the option B, that is given to us. Okay, so I hope this one is clear to you. Now the next question we have is this one. So phosphorescence is represented as, so we have the velocity diagram like this. We have different states of the excitation in which it takes place. This is the singlet ground state. This is the singlet excited state, and somewhere it lies the triplet state, that is T1. If the excitation is from S0 to the S1, this is called as the absorbance. Absorbance, right? If the particle it is returning from the singlet S1 state to the triplet T1 state, this is called as intersystem crossing. And if the particle is returning from the S1 to the S0, that is between the same states, if this excitation or it is returning, this is called as the internal conversion. And this intersystem crossing and the internal conversions, these both are the non-radiative processes. ISC and the IC, these both are the non-radiative. That means no light will be emitted in them, right? But whereas if you see from the S1 to the S0, if the particle it is returning, then in this case, if some light is being emitted from the state S1 to the S0, this is called as the fluorescence. This is called as fluorescence. Okay. Whereas if the particle is returning from S1 to the T1, so state change if it is there with the emission of some light, that is H nu, that is called as the phosphorescence. This is phosphorescence. So phosphorescence and the fluorescence, these both are the radiative processes. So in the phosphorescence, what we are seeing is particle is returning from the S1 to the state T1 along with the release of some of the light conditions. Okay, so that is represented in the option E. Next is we are having this. It says using a cuvette which is of 0.5 centimeter path length and this much molar concentration of a chromophore which shows 50% transmittance at a certain wavelength, the molar extinction coefficient in the units mole inverse, centimeter inverse, we have to find it out. We know absorbance, it is equal to epsilon into the C into the L. Absorbance is nothing but the negative log of the transmittance value, which is epsilon C into the length of it, right? So now the transmittance value, it is 50%, so 50 upon the 100, this is equal to epsilon. The concentration value, it is 10 raised to the power of minus of 4 and the length is 0.5 centimeters. So just solve this. This we are getting it as 1 by 2. This will become log of 2, that is equal to epsilon zero point 0.5 into 10 raised to the power of minus of 4 molar centimeter. So log 2 is nothing but the 0.310 upon the 0.5 into 10 raised to the power of minus of 4. Units of it will become molar inverse, centimeter inverse, that is gonna be your epsilon value. Solving this, the value of epsilon we are getting it as it is 6020 molar inverse centimeter inverse. So this is gonna be your answer. That is given to us in the option. It is 6020. So this is the answer in the option D. It is given to us. Right. Moving upon to the next one we have is this. So from for the 2012 June exam we have this. Now let us start with the CSIR December 2012 exam. The first question you have is if the concept of the half-life is generalized to the quarter life for a first order reaction, it will be equal to. So quarter life means T quarter, you have to find it out, which is T quarter, which means the remaining concentration it is A naught by the 4. Okay. So for the first order reaction, we know the integrated rate expression is ln of the A naught minus the ln of the A. This is equal to the Kt of it. Now for the quarter life, this condition we have to impose it. So it will be natural log of A naught minus the natural log of A naught by the 4, which is equal to Kt quarter of it. Right? So this we can write it as natural log of A naught upon the A naught by the 4, which is Kt quarter of it. So A naught and A naught will get cancelled out. Ln of 4 by the K, this is gonna be equal to your T quarter. So this is gonna be the answer, which is in the option B. It is given to us. Moving upon to the next one we have is this. The activation energy of a bimolecular reaction, it is A plus of the BC, this reaction it is given, whose activation energy is E naught in the gaseous phase. If the reaction is carried out in a confined volume of lambda cube, the activation energy is expected to. So what we are doing is we are decreasing the volume of it. So if the reaction is carried out in a confined volume of this much. So if you see, smaller is the volume you are having, more will be the probability of the molecules colliding with the one another and more will be the chances of the product formation, which means the activation energy of it will be lowered down, right? So smaller is the volume, more will be the chance of, more will be the chances of collisions, more will be the chances of collisions and lower will be the activation energy. Lower will be the activation energy. Right? I hope it is clear. Suppose initially you are having a larger one and then you are taking the same content in a smaller volume. So here what is gonna happen? The probability of collision between the particles it is gonna increase, hence the activation energy of the reaction it is gonna decrease. So we can say if the volume it is decreasing, then the activation energy also it is decreasing, right? So it has given activation energy is expected to, is it remaining unchanged? No. It increases with the decreasing. So is the activation energy increasing if the volume we are decreasing? It is the incorrect. The activation energy it is decreasing with the decrease in the volume, that is in the option C it is given to us. Right? Next one we have is this. It says the decomposition of the ammonia on a molybdenum surface follows the Langmuir-Hinshelwood mechanism. The decomposition was carried out at the low pressure conditions. If the initial pressure is this much, the pressure was reduced to this much in 10 minutes. What is gonna be the rate constant for this? So here at the low pressure conditions, the first order it is obeyed. The first order kinetics we are gonna observe it. So that means according to the first order we have that P naught, that is initial pressure, it is given to us as 10 raised to the power of minus of 2 torrs, and the final pressure it is 10 raised to the power of minus of 4 torrs. The time it is given to us as 10 minutes. Now for the first order kinetics we know that P is equal to P naught times E raised to the power of minus of kT of it. So this is 10 raised to the power of minus of 4. This is equal to 10 raised to the power of minus of 2 e raised to the power of minus of k, and the time is of the 10 minutes. Right? So this becomes 10 raised to the power of minus of 2. This is equal to e raised to the power of minus of the 10k. Right? So this will become natural log of 10 raised to the power of minus of 2. This is equal to minus of the 10k of it. So this you can take it on the other side, which will be minus of the 2 natural log of 10, which is equal to minus of the 10k. This 10 and 10 will get cancelled out. 2 into the 2.303 log of 10, which is unity, upon the 10 will give us the rate constant value. So this is gonna be equal to 4.606 upon the 10, which we will be getting it as 0.4606 minute inverse. So this is gonna be your answer. 0.4606 minute inverse. Option B will be the correct answer in this case. Next is, this was all about the year 2012. Now moving upon to the next one, which is for the 2013. Firstly, it is for the June, the exam that was conducted. So it says in the atom recombination reaction. So what is atom recombination? Suppose two of the atoms A and B, A and A only they are having, two of the atoms we are having, and they are combining to form the A2. So this is what is happening. So two of the atoms they are combining. So from two you are going into the one of it, one of the molecule you are going, which means the entropy of the system it has decreased. That is the degree of randomness which we measure as the entropy from the 2 if we are going to the 1 it is decreasing, which means the delta S for the reaction it is negative, it has decreased, right? And whenever the, now here A and A you were having, in between them a bond has been formed. So whenever a bond is getting being formed, energy is released during the course of reaction. During bond formation, bond formation energy is released, energy is released. For bond breaking energy is required, but during the bond formation energy is released, which means the delta H for the reaction it is gonna be negative because the reaction is exothermic in the nature, exothermic in the nature, right? So delta S is negative, delta H is negative, and about the activation energy for the atom recombination reactions, activation energy is zero always. So EA is zero, delta S is negative, delta H is negative. Option B will be the correct answer in this. Okay. Next is you have this one. It says a radioactive isotope of the argon 14. It is decaying at the rate of 34500 in disintegrations per minute, but decay it falls to 21,500 disintegrations per minute after the time t. What is the t half value for this? Okay. So radioactivity, first order kinetics are being formed. The initial decay it is given to us, which means you can say the initial activity it is given and the final activity is given. We know that n is equal to n naught times e raised to the power of minus of kt of it. The final disintegrations we are having is 21500. Initial one we are having is 34500 e raised to the power of minus of the k. The time period is of the 75 minutes. So just solve this and find the value of the k in this case. So it is 21500, 34500 natural log. This will be equal to minus of 75 into the k of it. So k value we will be getting it as 0.006309 in this case. Okay. Now you have to find is the t half value which is equal to 0.693 by the k. So this will be 0.693 upon 0.006309, which comes out to be as 110 minutes. So this is the t half value. So the correct answer is the option B in this case. Okay. Next one you have is this. It says observe the following statements. So out of these three, we have to tell which one is the correct one. So in the H2O2 reaction, explosion it occurs when the rate of the branching is exceeds the rate of the termination, which means rate of branching, it means the propagation that is taking place, propagation step that is involved. It is more as compared to the termination, it is more as compared to the termination. So in the H2O2, what is happening? The reaction it is propagating, that is going in the forward direction, but the species that have been getting formed, they are not terminating. All of them, they have not terminated. So reaction obviously will lead to the explosion. So this statement is your true one. Okay. Next is the order of the reaction, which is this one. It is 2.5. For this reaction, T half value, it is proportional to A naught raised to the power of minus of 3 by 2. We know this thing that T half, it is equal to 2 raised to the power of n minus 1 minus of 1 upon the n minus of 1 into A naught raised to the power of n minus 1 into the rate constant k. This is for the nth order kinetics. T half general expression we have it. So from here T half it is inversely proportional to A naught raised to the power of n minus 1. So now here the order it is given to us as a 2.5. So this becomes 2.5 minus 1, which is 1 upon the A naught raised to the power of minus of this raised to the power of 1.5, which is A naught raised to the power of minus of 1.5, which is nothing but the A naught raised to the power of minus of 3 by 2. So this statement is your true one, right? Next is unimolecular gaseous reactions. They are second order at the low pressure, but it becomes the first order at the higher pressure. So this statement is also the true one, because for the unimolecular reaction, the rate expression you get it, it is K1 into the K2 into the A square upon the K inverse of the A plus of the K2 plus of the K2. So they are saying at the low pressure, at the low pressure, which means K2 is much greater than that of K inverse of A. Using this in the above expression, we will be getting rate will be equal to K1 K2 into the A square up on the, now K2 is much greater, so in the denominator you have is K2 only, so this gets cancelled out, so the rate expression will be K1 into the A square only. So rate is proportional to the A square, that means it is of the second order kinetics, right? At the high pressure, this is at the low pressure, at the high pressure conditions also you can see the rate was K1 K2 into the A square upon the K inverse of A plus of the K2 of it. So if K inverse of A is greater than that of the K inverse of A is greater than that of the K2, that means this is at the high pressure conditions we are talking about. At that point, rate will be equal to K1 K2 into the A square upon the K inverse of the A. So with this A1 of the A, it will get cancelled out. It will become K1 K2 upon the K inverse of it into the rate constant into the A. So you can see rate is proportional to A's concentration raised to the power 1, which means it is following the first order kinetics. First order kinetics. Right? So this statement, it is also your true one only. Okay. So all these statements 1, 2 and 3 are the correct. That is in the option A we are having. Okay. Next is we have this question. So again, a repetitive type of equation is there. Data is given to us and the time period is given. We have to find the order of the reaction. So integrated rate expression, rate law expression has to be used. The data that is given to us and the time period. Data it is 1, 0.5, 0.33 and the 0.25. Time period we are having it as 0, 1, 2 and 3 seconds. So this is the time period. Let us check it firstly for the, if it is following the zero order kinetics. Just like the previous question we did, firstly for the zero order kinetics we will be checking that if the rate constant it comes out to be the constant using the datas. Then if the reaction is following the zero order kinetics, if it is not so, then check for the second order firstly and then you can check for the first order. Okay. So according to the zero order, the integrated expression is A naught minus of A, it is equal to the Kt. The initial concentration I am having it as 1. The remaining concentration we are having it as zero point 0.5. This is the rate constant K. The time period is of the 1 second, which means the rate constant value I am getting it as zero point 0.5 in this case. Right? Using the second data, that is 1 and zero point 0.3. Again, A naught minus of A is equal to the Kt. A naught value it is 1 minus of 0.33. It is equal to the rate constant K and the time it is of the 2 seconds now. So it will come out to be as 0.66 upon the 267 it will come is equal to the rate constant K. This comes out to be as 0.3 something it is coming out. So you can see one time we are getting it the value as 0.5 and other time the value as 0.33. The K value is not the constant one. So this is not following the zero order kinetics. Now check it for the second order kinetics. For the second order, we have the expression 1 by A minus the 1 by A naught. This is equal to the Kt. Okay, so 1 by E, it is 1 by zero point 0.5 minus the 1 by 1, this is equal to K, time is of the 1 second. So this is 10 by the 5, 2 minus of 1, K value will be equal to the 1 in this case. Using the other data, the other rate, the other A naught A value which is 0.33 minus of the 1 by 1. This is equal to the rate constant K. Time here is of the 2 seconds we are having it. So solving this, the rate constant we will be getting it as 1.015. So you can see 1 point something and 1 value you are getting. So K value you are seeing it as your constant. So that means reaction is of the second order kinetics. Okay. So the answer will be the option A in this case. Right. Moving upon to the next one we have is this. It says that in a Lindemann mechanism of a unimolecular reaction, the observed rate at a low concentration. So for a unimolecular reactions we are having rate value is K1 K2 into the A square upon the K inverse of A plus of the K2. Right. At the low concentrations if we are talking, so that means K2 is greater than that of the K inverse of the A. So rate will be equal to K1 into the K2 into the A square upon the K inverse. K2 it will be there because K inverse of A is smaller one. So K2 and K2 gets cancelled out. Rate expression we get it as K1 times the A square. So this is following your second order kinetics. Because A square value it is there. Second order. The correct answer will be the option D in this case. Right. Moving upon to the next one we have is this. It says a bacterial colony it grows most commonly by the cell division method. The change in the population due to the cell division in an actively growing colony it is given like dn that is equal to lambda into the n into the dt. The population of the bacterial colony at the time t it is gonna be, so you can take this dn, this n factor it is brought in the denominator. This is equal to lambda times the dt of it. So after the time t you have to find it out. So integrate on both the sides. Integrate on both sides. We are getting it dn by the n. We are going from the initial concentration that is n naught to the final concentration at time t which is nt. This is equal to lambda into the dt. Time is going from 0 to t. Alright. So this is natural log of the n we will be getting. Limits are from n naught to the n. This is equal to the lambda times the t that is going from the 0 to t. Right. So just put the limits now. Natural log of the n minus the natural log of the n naught. This is equal to the lambda times of the t. Right. So we can say natural log of n by the n naught. This is equal to lambda times dt, or n by the n naught is equal to e raised to the power of lambda t, or the concentration which is after the time t that we are getting, that is n. This will be equal to n naught times e raised to the power of lambda t. So this will be the concentration of the bacterial growth after the time t periods, that is n naught times exponential of lambda t, which is given to us in the option B. Right. Next one we are having is this question. It says the rate equation for these reactions. The rate is given by this one. A possible mechanism for the given with the given consistent with this rate law. So rate expression, if you see here the term AB and B2 is involved, both of them they are raised to the power of the 1 and 1. Through the options you check it. Here the option 8 says AB and B2 are involved. Reaction is following the slow rate, but here the stoichiometry 2 is present in front of the AB, so this is not the correct one. Next is in the option B, slow rate it is dependent on the A2 and the B2 terms, but this A2 you can find it from this equilibrium expression. So AB square something you will be getting it. So that 2 is not involved. Here only the AB is raised to the power of the 1 only. So this is also not the correct one. C option, if you see, the slowest step of the reaction is this one, and where the terms involved are AB and the B2. That means this is gonna be the correct answer because the rate of the reaction is dependent upon the slowest step involved in the given reaction. So C will be the correct answer in this case. Okay. Moving upon to the next one we have is this question. It says a 0.1 molar solution of a compound showing the 50% transmittance when the cell of when a cell of the 1 centimeter width is used at lambda 1 nanometer. So this much wavelength you are having at that point, transmittance is this much. And another zero point 0.1 molar solution of the compound which gives the optical density, which means the absorbance value of this much using the 1 centimeter length at the lambda 1 same wavelength in the nanometers. What will be the transmittance of a solution that is simultaneously zero point 0.1 molar in A and zero point 0.1 molar in B using the same cell and of the same wavelength? So now here a mixture of both of this they are obtaining it. Now we have to find is the transmittance value. A transmittance we know it is multiplicative in the nature, multiplicative in the nature, whereas the absorbance value, if you see, it is additive in the nature. It is additive in the nature. So what we are doing is we are finding the absorbance for both of the solutions and then the overall absorbance, which is gonna be the sum of the solution A absorbance plus the sum of the solution B. You can directly find the transmittance values also or the absorbance value. Both of them can be used. Okay. So absorbance for the A solution, it is negative log of the transmittance value of it, which we are having it as negative log of 50%, which is 50 by the 100 we are getting it. And for the solution B, the optical density, it is given to us as 0.1761. So this you have to just add it. So this is log 2 it will become, that is 0.3010 plus of the 0.1761. This we will be getting the value as 0.4771. This is gonna be the overall absorbance of the solution that you have obtained. Okay. Now we know that this absorbance value, it is equal to the negative log of the T. So this transmittance value you have to find for the overall mixture of the solution A and B. Absorbance, it is 0.4771. This is equal to the negative log of the T. So transmittance you can find it from here, which is 10 raised to the power of minus of 0.4771. Solving this, we are getting the value as 0.3333, but in the percentage, transmittance percentage, it is gonna be 33.33% of it. So the correct answer will be the option A in this case, 33.33%. Okay. So now moving upon to our next question that we have is this one. It says a chemical reaction which is involving a non-linear molecule combining with the non-linear molecule which is in equilibrium with the non-linear activated complex. The number of vibrational degrees of freedom in the activated complex containing the n number of the atoms we are having it. So here it is non-linear plus the non-linear. This is in equilibrium with the non-linear one. With the non-linear one. So in general, we write it. This is not for the activated complex. In generally, if we talk about in general, we say that there are for the linear molecules, number of the vibrational degrees of freedom we have is 3n minus of the 5. Reason being, you have 3 translational degrees of freedom, 3 translational and 2 rotational degrees of the freedom. So these 5 in total, it is subtracted from the total, which is 3n total degrees of freedom that you have, it is 3n. So 3n minus of this 5 gives you the vibrational degrees of the freedom, right? Whereas for the nonlinear molecules, we have total degrees of freedom is 3n only. Translational, it is 3, whereas the rotational also it is equal to the 3 only. So 3n minus of the 6, this is in general we have the vibrational degrees of freedom for the non-linear molecules. But for the for activated complex theory, activated complex theory, we have one loose vibrational degree of freedom. This was an assumption made in this. We have one loose vibrational degrees of the freedom. So that degree of freedom, it has to be subtracted from the total. That is for the activated this theory if you will be talking about. Here in the case of linear, here the number of the vibrational degrees of freedom, it will be 3 n minus of 6. Whereas for the non-linear one, it is gonna be 3 n minus of the 7. So they are asking us for this activated complex, the number of the vibrational degrees of freedom. So in the nonlinear molecule, so the 3 n minus of 7 we will be having it. So the correct answer is the option C in this case. Okay. Next is you have this. So this was all your questions from the June 2013 exam. Now comes for the December exam conducted in 2013. The question we are having is, according to the Arrhenius equation, the plot we have been asked. Arrhenius equation we have that rate constant K is A, e raised to the power of minus of EA by the RT. Now with respect to natural log it is being asked. So take the natural log on both the sides. ln K is equal to ln A minus of the EA by the RT of it. So if I see a plot for natural log of k versus the 1 by t, so y is equal to mx plus of bc. So the plot we will be getting it like this. This is natural log of k versus the 1 by t. So a decreasing slope, with the decreasing slope the plot we are getting of the straight line with the slope value as minus of EA by the r, and this is the intercept value which is natural log of k, right? So we can say that ln k, it is decreasing linearly with the 1 by t. So k, if ln k decreases linearly with the 1 by t, that is in the option A it is given to us. Right? Now the next question we have is this one. It says for a first order gaseous reaction, it is 25% complete in 30 minutes at this much temperature, and it is in 10 minutes completed when the temperature you are taking it as 237 degrees centigrade. The activation energy of the reaction it is closest to. So two of the rate constants have been given, rate constants, this time expressions have been given that can be related to the rate constants and the two temperature conditions. So from the Arrhenius concept again it is there. So we know that natural log of K2 by the K1, this is equal to the EA by the R into the 1 by T1 minus of the 1 by T2 of it, right? So here it is saying the reaction is 25% complete in 30 minutes and it is 10 in 10 minutes it is completed at this much temperature. So we know that rate constant values, they are inversely proportional to the time. More is the time the reaction is taking to get completed, smaller will be the rate for it or the rate constant for it. Okay, so that means you can say one of the temperature you are having it as 500 kelvins and this one is your 510 Kelvin temperature you will be having it. So K2 value that you are having, it will be ln of K2, that is the time T2 which we are taking it, that is at 510 Kelvin, which is of the 10 minutes. So that will go in the denominator of it. And for the K1, 30 minutes time you are taking, so that is gonna come in the numerator. This is equal to activation energy EA upon the 8.314 joules per mole per Kelvin of it. Temperature T1 we are having it as 500 Kelvin and this one is 510 Kelvins of it, right? So just solve this. The activation energy value you will be getting is as 55.9 kilocalorie per mole. So in calories if we are finding it, so instead of this 8.314, you will be having the value of the R as 2 calories per mole per Kelvin of it. Okay. So the answer is 55.9. So approximately 55, the closest answer. That is the option C at 20. Right. Next one is this question. So this is in a reaction between NO and H2, following data is obtained. The first experiment was carried out where the hydrogen pressure was kept to be the constant, and the second experiment that was performed in that the pressure of the NO it was kept to be the constant. So here the method that we will be using, because one when more than one reactant terms are involved, to find the order with respect to one of them, you have to keep the concentration of the other to be the constant one, right? So this method it is called as the ratio variation method. Ratio variation method. Right. So here from the first experiment, here the value of the pressure it is given to us, and here this rate expressions have been given to us. If you take this data, which is 0.25 and 1. So you can see the rate it is becoming approximately the 4 times, when the pressure it is approximately the 2 times. So how we are writing the rate for this? It is dependent upon the pressure of the NO and raised to the power of alpha, and the pressure of the hydrogen raised to the power of beta of it. This alpha and beta terms we have to find it out. Okay. So first time the rate value it is taken as 1.03. When the pressure of the NO it is my 300, it will be raised to the power of alpha. Pressure of hydrogen you can keep it like this only, beta, and the other rate we are taking it as 0.25. When the pressure of the this NO we are having it as 152. This is raised to the power of the alpha, and the pressure of hydrogen is still taken to be the constant, so that we can write it like this. So these two will get cancelled out if you take the ratios of these two rates, right? So this is becoming 4 times approximately, and this is 2 raised to the power of alpha of it. So this is R1 ratio. R2 you can say. So 2 raised to the power of 2, this is equal to 2 raised to the power of alpha of it, which means the order with respect to the NO is the 2 over here, right? Now similarly you can find it for the hydrogen. How is that varying? So for this the other data experiment was carried where the pressure of the NO was kept to be the constant. So here if you take this one and this data, so this is becoming approximately 2 times of it, and the pressure in that case it is also approximately the 2 times of it, right? So here the pressure, here the rate 1 and the rate 2 we can write it like this. Pressure of the NO we are keeping it to be constant. Here also pressure of NO it will be constant. The first time the rate we are taking it as 1.60, and the other time we are taking it as 0.79. When it's 1.60, the pressure of the hydrogen you are having it as 289, and here it is 147. So here it will become 2 times of it. This is raised to the power of beta of it, because these twos were raised to the power of beta. So 2 raised to the power of beta is equal to 2 only. So beta value we are having it as 1, which means the pressure with respect to the hydrogen it is 1, and with respect to the NO it is 2. So 2 with respect to NO and 1 with respect to the hydrogen, which is given to us in the option B. Right? Now moving upon to our next one, that is for the year 2014, the June exam. Okay. So this question is from your consecutive reactions. So steady state approximation is being applied over it. So steady state approximation we can apply it when K2 for the reaction it is much greater than that of the K1 of it. What this K2 and K1 is there? Suppose A to B you are going and B to C you are going. This is the rate constant K1 and this is the rate constant K2. When in case K2 is much greater than that of K1, in that case SSA can be applied. So in the option A, if you see, K2 is 10 raised to the power of 8 and K1 is 10 raised to the power of 5. So this condition of the SSA it is getting being satisfied. K2 is much greater than that of the K1. In the B option, if you see, K1 is 10 raised to the power of 5 and K2 is 10 raised to the power of 3. So K2 becomes the less than the K1. So this won't be satisfying this. Option C, both of them are equal. That also in this condition SSA can't be applied. Option D, 10 raised to the power of 2 and 10 raised to the power of 6. Again K2 is greater than that of the K1. So SSA can be applied. So A and D, option D will be the correct answer. Okay. Next one we have is this question. It says that in a Lineweaver work plot, that is for the 1 by R versus the 1 by S for an enzyme catalyzed reaction following the Michaels-Menten mechanism, the value of intercept is this much. If the initial enzyme concentration is this much, what is the turnover number? So turnover number is nothing but the K2 value you have to find it out. Okay. So here we are having the according to the enzyme catalyzed reaction, you have R is equal to the R max into the S upon the Km plus of the S of it. This is the expression we have it. Now 1 by R, it will be equal to the Km plus of the S upon the R max into the S of it. This is R max into the S of it. So this X and S, this S will get cancelled out. We will be having Km upon the R max into the 1 by S plus of the 1 by R max of it. Right? This is equal to the 1 by R of it. So the plot is for the Y is equal to the Mx plus of the C. So from here the slope value, which is Km upon the R max, this is given. This is not given to us. Okay, this is the slope value and the intercept is 1 by the R max. This is your intercept and its value, it is given to us as 5000 molar inverse. So which means 1 upon the R max. This is equal to 5000 molar inverse. So now R max is nothing but the K2 into the E naught of it. So this is equal to 1 upon the initial enzyme concentration, it is given to us K2 into the 10 raised to the power of minus of 9. This is equal to the 5000. So as I said, turnover number, this is nothing but the K2. So this K2 value you just have to find it out. This will be 1 by 5000 into 10 raised to the power of minus 9 of it. So solving this, the value we will be getting it as 2 into 10 raised to the power of 5 of it, which is your K2, that is your turnover number. So the correct answer becomes the option D in this case. Okay. Moving upon to the next one, we have is this question. It says the fluorescence lifetime of a molecule in a solution is this much. The fluorescence lifetime is tau f value, it is given to us as 5 into 10 raised to the power of minus of 9 seconds of it. The sum of all the non-radiative rate constants, which means the rate constant, that is internal conversion plus the internal intersystem crossing, their sum, it is given to us as 1.2 into 10 raised to the power of 8 second inverse. This is the value. What is the fluorescence quantum yield? So fluorescence quantum yield, this you have to find it out, which is nothing but the Kf into the tau f of it. So now Kf value we are not having. Using the above data, we will be finding the Kf value firstly. So tau f value, it is equal to 1 upon the Kf plus of the Kic plus of the Kisc. So this is the value. Now tau f value we are known, that is 5 into 10 raised to the power of minus of 9. This will be equal to 1 by the Kf plus of this, these two sum, which is 1.2 into 10 raised to the power of 8. Alright. So using this, the Kf value we can find it out. 1.2 into 10 raised to the power of 8. This is equal to 1 upon 5 into 10 raised to the power of minus of 9. So this will become 0.2 into 10 raised to the power of 9 of it. So this decimal we can take it. So 2 into 10 raised to the power of 8. This is the value. Now from this we have to subtract the values of the 1.2. 2 into 10 to the power of 8 we got it. From this 1.2 into 10 to the power of 8, if we subtracted 0.8 into 10 raised to the power of 8, this is the kf value we are getting it. Right? Now quantum yield, it is equal to the tau f into the kf of it. Tau f value we are known, that is 5 into 10 raised to the power of minus of 9, and the kf value we have calculated as zero point 0.8 into 10 raised to the power of 8 of it. This decimal you can remove it. 5 8s is 40. So 110, no, this 0 will go. 4 into 10 raised to the power of minus of 1, which means it is 0.4. So this is gonna be the quantum yield value. So the option, if you see, that is in the option C, it is given to us. Right? So this is how this question has to be solved. Now moving upon to the next one, we are having this question. It says for a first order reaction A to P, A2 products, the plot of AT by the A naught versus the time where A naught is the concentration at time t is equal to 0 and AT is the concentration at time t is equal to t. For the first order reaction, we know that A is equal to A naught times e raised to the power of minus of kt of it. Now A by the A naught, this is equal to the e raised to the power of minus of kt, or natural log of A by the A naught, this is equal to the minus of kt of it. So in this expression, which is natural log of A upon the A naught, this is minus of the kt. So if I make a plot for the natural log of A by the A naught versus the time t, so y is equal to my mx, right? So the slope value I am getting it as minus of k, which is the negative value. So the plot, if you see, it's gonna look like this. So the natural log of A by the A naught. Y is equal to mx, so intercept value is 0 in this case. So that is gonna, the time you are having, it's gonna look like this. Intercept value is 0, a negative slope. So it will be starting with the from the origin with the slope value of minus of k. Okay, so the graph is a straight line with the negative slope which is passing through the origin, that is in the option B, it is given to us. Right, now moving upon to the next one. So that is from the December 2014 exams. Okay, so the first question we have is that for an enzyme substrate, the plot between 1 by V versus 1 by S naught, that is again from the Lineweaver-Burke plot. If the enzyme concentration is this much, what is gonna be the catalytic efficiency in this case? So eta value we have to find it out. The slope value it is given to us. So again, the enzyme catalyst reaction, the rate we have is R is equal to R max into the S upon the Km plus of the S of it. 1 by R, it will be equal to Km plus of the S upon the R max into the S of it. So we can write it like this: 1 by R, it is equal to Km upon the R max into the S of it plus of the 1 by R max of it. Right, so from here, if you compare it with your straight line equation, y is equal to the mx plus of the c. So slope value we are having it is km by the r max of it. Right, slope is given to us as 40 seconds. Right, so r max now it is nothing but the k2 into the t naught of it, which is equal to the 40 seconds. Right, so we have to find this efficiency which is equal to K2 by the Km of it. So K2 by the Km, it becomes 1 by E naught into the 40 seconds. So initial concentration, it is given to us as 2.5 micromolar. So that is 10 raised to the power of minus of 6 into the 40. Right. So just this decimal it will come. This gets cancelled out. So 25 fours are, it is 100. So it becomes 10 raised to the power of minus of 4. It's going in the numerator. It will become 10 raised to the power of 4. The units will be liter per mole per second of it. Liter per mole per second of it. So 10 raised to the power of 4, that is given to us in the option D. Right. Now next is we have this question. It says that for a gaseous reaction, which is 2NO plus Cl2, giving you the non-linear transition state and then to the final product. So we are having this 2NO plus the Cl2. This is giving you the non-linear transition state. The pre-exponential factor for this rate constant is proportional to. So for this we know the pre-exponential factor, it is equal to the kBt by the h into the x bar, which is x bar, we are having this. It is the partition function of the activated complex upon the partition function of the various reactant terms. Here the reactant terms we are having is 2NO and 1 Cl2. So this will be partition function of NO into the partition function of NO into the partition function of Cl2. Now this NO and Cl2, all of these three, they are your linear molecules. These are my linear molecules. So for the this activated complex, which is your non-linear, you will be having the translational partition functions. Three of them it will be there, so it is raised to the power of 3. So this is translational. Next is partition function for the rotation. Non-linear molecule, it has three of the rotational degrees of freedom. So 3 it will be there. Now for the linear molecules, we will be having for the NO 3 translational degrees of 3 raised to the power of 3 partition function, and for the rotation it will be 2. Similarly for the other NO, 3 translational we are having and the 2 rotational values we are having. For the Cl, again the partition function for the translational raised to the power of 3 and that of the rotation raised to the power of 2 we will be having it. Right. Now each of this translational functions, partition functions that you are having, it is raised to the power of, it is proportional to T by 2. So this will be equal to, for the translational, it will be temperature raised to the power of 3 by 2 of it. Rotational also temperature raised to the power of 3 by 2 of it. And in the denominator we are having this. So all of this, they are temperature dependent. So this one you are writing, and for the denominator also, t raised to the power of 3 by 2, it will be t raised to the power of 2 by 2, t raised to the power of 3 by 2 into t raised to the power of 2 by 2, and again t raised to the power of 3 by 2 and t raised to the power of 2 by 2. Right? So from here 1 t raised to the power of 3 by 2, and this will get cancelled, this and this will get cancelled out. So this is the x value you will be getting. So a value you have to find it out. Here it is T1 more, it is there. So that has to be included in this. So it will become, in the denominator we have is 1, 2 and 3. So 3 plus of 3 by 2. So 6 plus 3 we are having is 9 by 2 in the denominator. T raised to the power of 9 by 2 we are having. So if you take this, so A we are seeing it is proportional to T raised to the power of 1 minus of 9 by 2, which means it is A is proportional to T raised to the power of minus of 7 by 2. So this is the pre-exponential factor that is gonna be proportional to T raised to the power of minus of 7 by 2, that is given to us in the option D over here. Right? So this is gonna be the answer. Now next one we have is this question. So rate constant for a reaction which is raised to the power of 3 plus and B raised to the n positive. It is measured at two different aqueous solutions of the ionic strengths and this and this. So this question is from your primary salt effect. Primary salt effect, which means the reaction carried out into the aqueous solutions. So for the primary salt effect, you have the rate expressions like this, you get it. Log of the K, it is equal to log of K naught plus of the 2A times the ZA, ZB. These are the charges which are present upon the ionic species which are being involved into the root of their ionic strengths. Okay, so now here the reaction is carried out when the ionic strength is firstly it is 0.01 molar and at the other time it is 0.04 molar. So it is log of the K 0.01. This will be equal to log of the K naught plus of the 2A into the ZA, which is plus 3 charge that is present upon the A, and N plus, which is the charge on the B component that we are having, into the root of ionic strength, which is 0.01, and the log of 0.04. This is for when the rate constant it is 0.04 when the different ionic strength you are using. This is equal to the log of K naught plus of the 2A times the Z positive, which is plus 3 into the plus N, right, into the root of the ionic strength, which is 0.04, right. So just subtract these two because the rate constant ratio you are having is log of the K, that is for the 0.04 upon the 0.01. So subtracting these two, log of the rate constant when the ionic concentration is 0.04 minus of the log of the K when the ionic strength we are having it as 0.01. This will be equal to log of the K naught plus of the 2A, this is 3N into the root of ionic strength, which is 0.04 minus of the log of K naught plus of the 2A into the plus 3N into the root of the ionic strength, which is of 0.01. So this log K naught and K naught values it is getting being cancelled out. On the left side it becomes log of the K, that is of 0.04 upon the rate constant of 0.01. This is equal to 2A times the 3N into the 0.04 root minus of the 0.01. This is what we will be getting. So this becomes where the 2 by 10 minus of 1 by 10 into the 2A times the 3N value, right? This rate constant's ratio value it is given to us as 0.3, right? So now A value we have it as 0.5. Now 2 into the 0.5, it will be unity. It will be 3N into the, this will become your 1 by 10, right? So this is equal to your 0.3. So we are getting it as 0.3. It was equal to 2 into the 0.5. It will become unity. It will be 3N into the 1 by 10. So that means this 10 you can bring it over here. This 3 and 3 will get cancelled out. 10 and 10 will get cancelled out. So N value we are getting it as 1. So that means the charge on the cation B that you are having, it is nothing but the plus 1. So E is gonna be the correct answer for this one. Okay. Now moving upon to the next question you have is this one. It says the species A, it undergoes a unimolecular reaction. It follows as follows. Okay. For this reaction, the first order rate constant at high pressure it is K infinity. The first order rate constant it becomes K infinity by the 2 when the pressure of A is A half. The values of the K1 it is gonna be okay. So this is the graph that is given, that is for a first order reaction for the plot of rate constant versus the pressure. Where when the maximum pressure you are reaching the rate constant value, it is given as to be the K infinity. So this is from the Lindemann mechanism of the unimolecular reaction that we have. Lindemann mechanism. The equations that are given, this is for the Lindemann mechanism only, which is K plus of the A, they are combining with the rate constant K1, K inverse giving us activated complex plus of the A, and then this activated complex with the rate constant K2, this is giving you the product P. Okay, so the rate expression for this we have it is K1 into the K2 into the A square upon the K inverse of the A plus of the K2 of it. This is the rate expression we get, but this is the mechanism that we have written. But in actual the reaction, what we observe is observed rate constant. For that we can write it, that is A giving you the product P. The rate constant is K dash for it. So the observed rate, that is equal to the K dash into the A of it, right? So these two rate expressions you can equate it. So from that, the observed rate constant value that we get, it is gonna be equal to K1 into the K2 into the A upon the K inverse of A plus of the K2 of it. This is what we will be getting. Now, if I take this reaction at the high pressure conditions, at the high pressure, which means K inverse of A, it will be greater than that of the K2. So observed rate constant at that point, it will become K1 into the K2 into the A upon the K inverse of the A, right? So this A and this A will get cancelled out. So K dash at that point we are having it as K1 into the K2 upon the K inverse. This is already given to us that the first order rate constant at higher pressure, it is nothing but the K infinity. So K infinity is nothing but this ratio, that is K1 into the K2 upon the K inverse of it, right? So now we are having this expression for the observed rate constant, which is K1 into the K2 into the A upon the K inverse of the A plus of the K2. This is the expression you are having. If you take the this condition, which is K inverse of A, that is equal to the K2 of it, and at this point the A's concentration, it is A half that we will be having it. Okay, this is what they are asking, that the first order rate, it becomes K infinity by the 2 when the pressure of it is A 1 by 2 you are having it. So how is it becoming 1 by 2? That also you will be seeing, and from that we will be finding the K1 value. Okay, so these condition when you are having, that is K inverse of A is equal to K2. So from this you can make two of the cases. So first time, if I substitute the value of the K inverse of A in place of the K2, at that point the K dash, it will become K1 into the K2 into the A upon the 2 times the K inverse of the A. This expression we will be getting. So this A and A term will be getting cancelled out. This you can write it as A half. So no need for that. They are getting the cancelled out. So we will be getting the K1, K2 upon the K inverse, and this is 2. This is nothing but your K infinity by the 2. So this is true. One of the conditions you are getting the observed rate constant. Now the other case, if you substitute the value of the K2 instead of the K inverse of A, at that point the K dash, it will become K1 into the K2 upon into the A half you are having upon the K inverse of A. Instead of that you are using is the K2. So K2 and K2 will get cancelled at that point. This is equal to K1 into the A half upon the 2. This is the observed rate constant. So here we are seeing that K inverse, this was equal to the K infinity by the 2. So that we can use it in this case, that we have got K observed, it is equal to the rate constant K1 into the A half upon the 2. This is nothing but the K infinity by the 2, right? Because this thing we have obtained it from here. So equating these two, if you see 2 and 2, it's getting being cancelled out. So from here, the K1 value we can get it as, we will be having K1 into the A half. This is equal to your K infinity. That means the K1 value, it is K infinity by the A half. So this is gonna be the rate constant K1 value, right? So this is what was being asked, the value of the K1 it will be. This is value of the K1, it's gonna be K infinity by the A half, that is in the option A it is given to us, right? So I hope this whole process that I have followed it is clear to you. Now moving upon to the next one we are having is this question. It says a reaction which is A plus B is giving you the A plus B plus C is giving you the B. It is following the mechanism which is A plus B is in equilibrium with the AB and AB plus C it is giving you the product D, in which the first step it remains essentially in the equilibrium. Okay. If delta H is the enthalpy change for the first reaction, for this the enthalpy change is delta H, and E naught is the activation energy for the second reaction. So what is the activation energy of the overall reaction? So how is basically this reaction proceeding? So here if you see the reaction progress, and here is this energy. So initially these reactant terms they are in the equilibrium and forming the intermediate which is the AB, and then this AB with some activation energy for these reactants, this is forming an intermediate, and with some activation energy E naught they are forming the final product B, right? So initially and having the reactants which is A plus BP, they are forming the AB, and this AB it is combining with the C and forming the product which is my D. So in the first case it is given that for the first step the enthalpy change we are given, that means this value it is given to us which is H naught delta H it is given to us, and for the second step the activation energy, so this is the activation energy from this side to this side, what is this total energy that is required to complete the reaction, this is the activation energy. So overall activation energy required for this whole process will be the sum of these two, because from here we are reaching to this product D. So for that we need to complete this activation energy, we have to find it out, which is the EA value. So EA value it is nothing but the sum of this enthalpy change that we are having, and along with that the activation energy that is required for the second step, right? So the answer will be T naught plus of the delta H. So C is the correct answer in this case. So this delta H value here it is starting from this K point only, this one, right? So up to here, right? So this is delta H plus the T naught value. Okay. Moving upon to the next question we have is this one. It says which of the followings will result in the deviation for the Beer's law. So the Lambert-Beer law that we obtain, the Lambert-Beer's law, that is for the observance that we see. It is for the dilute solutions. It is for the dilute solutions. To measure the observance, a monochromatic beam of light has to be used. Monochromatic means a single wavelength light. Monochromatic light has to be used. And the third thing, that is there should be no association or the dissociation processes it should be involved in it. No association or dissociation should take place, or the dissociation should take place, should take place. So these are some of the conditions for the Lambert-Beer law. So the 1, 2 and the third one. So here it says which of the following will result in the deviation. Okay. first is change in the refractive index or the medium. It's true. With the change in the refractive index and the index or the medium, the deviation will be seen in the Beer's law. Next is dissociation of the analyte on the dilution. This again will result in the deviation. A polychromatic beam of light, if we are using, again it's gonna cause the deviation because monochromatic light we have to use it. Path length of the qubit, it does not cause any deviation in the Beer's law. Okay, so first, second, and third are responsible for causing the deviation. So the correct answer will be the option D over here, right? So this was the last question that was for the year 2014 December exam we are having it. So with this, the questions from your 2000 and year 2011, 12 and 12, 11, 12, 13 and 14. These all the years we are done with it. So this was the year 14. Yes. So from 11 to the 14, all the questions we have done from the topic that was your of the kinetics. Okay, so that is it for this video now. The remaining questions that is of the upcoming years, that is from 2015 to the year 2025. Each and every single question we will be discussing in the upcoming classes. So make sure you subscribe to the channel so that you can get notified whenever the next part of it is getting being uploaded, and you can practice it as much as possible. So thank you so much for watching. If you have understood the concepts, then do like to the video also and share it with your friends. Thank you so much for watching. Okay, I'll be meeting you in the next video now.